Record. Okie dokie. Now it feels weird sitting down here. I can see you guys still. All right. Just a quick reminder, right? We're not meeting for lab this week because I have to go see some puppies, my mom's puppies. That doesn't matter, but no, reminder, no lab meeting tomorrow. But if we want to, I can schedule a room for next week sometime during the week if you want some lab time. Just a couple of things here. Done. Let me grab this in here. I know I started the recording, but I'm having that. Okay, good. That moment. So I went to mark lab 2, but then I noticed that there were some that hadn't submitted their RMD or RMW file. An R file is fine as well, but since you're explaining things, then it might be nice to have an RMD or an RMW file. So if I made a little note beside your submission, then just resubmit and that's fine. All right. And then same thing here. I just want that RMD file. RMWs if you're writing in LaTeX. I don't know if you guys are doing that yet or just RMD file is fine. I don't care either way, but RMD is probably the one you're using. And so just make sure that's what you're submitting. And then I'll knit it on my computer, that's fine. I did post lab 3 instructions. Okay, so because of all our holidays and stuff, it's a little bit behind in terms of material, right? Because this is going to be chapter 2 material. Okay. So you're going to work through some sampling distributions, essentially confirming the central limit theorem, and then you're going to practice running a bootstrap. Okay. All this code exists in that download that you did, right? So just use that code, manipulate it to do what I'm asking you to do, right? I changed some things, right? Instead of 1,000, you're doing 1,500, that kind of thing, right? So just kind of get comfortable with that code. And that's what you're going to do for the lab this week, right? So just here's the instructions and you just do it. It's harder than it sounds. Okay. I also posted an assignment, which I think is due next Friday. Due next Friday. I think it should show up on your calendar, but if it doesn't, let me know. Okay. It is just multiple choice questions. I wanted to make some kind of more conceptual questions, but it's really hard and time consuming, so I'm not quite finished. So okay, I'll get these to you guys now, and then maybe I'll do a follow-up assignment. Okay. Good. So I'll just check because there are quite a few online here. Any questions? No. Okay, good. Now I can't see it anymore. Last day we finished and we talked about type 1 errors and type 2 errors, right? And so a lot of our kind of significance testing that we do is based around trying to minimize the probability of a type 1 error. Okay, so let's just do a quick review. When we conduct a hypothesis test, I'm just going to do HT, hypothesis test, right? We expose ourselves to two types of errors, right? Let's just kind of go back there to two types of errors, right? And sometimes, what does it say? Errors. I often find it helpful if I set up some sort of table, right? So the truth and then my decision, right? I might decide to reject H naught or fail to reject H naught. FTR, fail to reject H naught, right? Those are my two options, right? I either reject H naught or I fail to reject H naught. I don't know what the truth is. That's why we're doing this significance testing, but there is some truth out there. And so then if H naught is true, right, then I could be making a mistake if I am rejecting H naught, right, if H naught is true, or if H naught is false, then I'd be making a mistake if I fail to reject H naught, right? So if I reject H naught and H naught is false, that's fine, right? That's not a mistake. If I fail to reject H naught and H naught is true, that's not a mistake either, right? So those are good conclusions to make. If I reject H naught when H naught is true, this is what we call a type 1 error. If I fail to reject H naught, so that means I didn't have enough evidence to reject H naught, but really I should be rejecting H naught. That is a type 2 error. I'm just going to close the door. Earlier, when I was in the other room, someone walked down the hallway and was like, kitty, 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 kitty. And I wanted to know if there was a cat in the hallway. We didn't find out. But pretty. Did you ask him why he was doing that? No. I know, hindsight, I should have run out there and been like, is there a cat out here? But I didn't. But pretty funny. It's kind of funny to think. So now if I walk down the hallway, maybe I'll just be like, kitty, kitty, kitty. Okay, so a type 1 error is rejecting H naught when I shouldn't be rejecting H naught, okay? Which is there's a p-value probability of making a type 1 error, right? But before we go out and do our test, we say, I'm okay with an alpha level probability of a type 1 error, right? And so that's where the alpha level comes in. So the alpha level is the probability of making a type 1 error. Okay. So before I go out and I do any testing, I decide, okay, how comfortable am I with making a type 1 error? 0.05 is the default, right? And so then there's a 5% chance that I'm making a type 1 error. I'm rejecting H naught when I shouldn't be. Okay. The type 2 error is a little bit harder to attach a probability to, a probability of making a type 2 error. but it's usually just due to your sample size is too small to be able to detect that H naught is false, right? And so you just didn't have enough evidence to reject H naught, right? And so type 2 errors are usually due to your sample size not being large enough. Are usually due to small sample sizes, right? Not large enough to detect that H naught should be rejected. To detect that H naught, and I'm going to put it on the same page here, should be rejected. Yeah. So all our testing, right, is done trying to minimize the type 1 error. Yeah, significance testing, which is just hypothesis testing, right? Significance testing, it's just another term for it, is structured to minimize the type 1 error. Minimize the probability of making a type 1 error. Probability of making a type 1 error. The sample size we can't do much about. Usually that's not a problem in data science, right? We've got all this data, right? And so that's not really a concern for us. It's more the alpha level. So if we think about kind of our most common distribution that we use, especially if I want to visualize something, visualize a concept, I'm going to use the normal distribution. Okay. Then when I set the alpha level here, right, alpha is 0.05, let's say. So for a one-sided test, just to kind of narrow down the options here, right? What we said is, okay, if the p-value is less than 0.05, which means it's beyond this point, right? This critical value it's called, right? Then this area here is the p-value, right? The one-sided p-value. So here, these can still happen, the p-values, even when they're super, super small, right? Just because they pass this threshold doesn't mean that it can never happen, right? It's just very unlikely to happen, right? And so, and I feel like I had something that I wanted to say here. So these values can still happen, right? If H naught is true. So H naught is here in the center. Right? H naught is that mu equals some number, for example, or mu1 equals mu2, right? And so that's going to be in the center. And then everything else is done assuming H naught is true. So these values can still happen. Under H naught, right? But are unlikely. That's what it So p-values, we're still going to use p-values. We're still going to talk about p-values. There are some journals who now refuse. So p-values used to be, okay, we need the p-values. What's the p-value? Blah, blah, blah. So we used to be very focused on the p-values, but now there's some journals that are saying, nope, we're not even going to accept anything if you talk about the p-value, just because it can be so misleading, right? And so that's why I really want to emphasize that you kind of have to use your judgment as well, right? So if this p-value, sure, it passes this threshold, but if it just passed it, right, then you need to use your judgment and say, okay, well, it can still happen, right? So the 0.05 is a good kind of check-in point, but it's not like the be all end all. Okay, so in data science, we're going to use p-values to identify significant findings still, right? Significant meaning, do I have enough evidence to reject H0, right? So we will use p-values to identify significant findings. Right? Significant meaning have enough evidence to reject H0. But we will still need to use our judgment as to whether the significant findings have practical significance, right? So there's this difference between significant findings and practically significant, right? Need to use our judgment as to whether the significant findings have any practical significance. Oops. All right. If a process that takes 1,041 minutes is improved by 1 minute, that's not really that great, right? Whereas if a process takes 2 minutes and you improve the time by 1 minute, then that's huge, right? So it's still 1 minute, but it's the practical significance part, right? So if a process that takes, I guess as an example, that takes 1,041 minutes is improved by 1 minute, this has little practical significance. Right, presumably. So last day we talked about A/B tests. So that's just a generic kind of umbrella term for if you're comparing two groups, right? And we talked about permutation tests. In terms of those, we throw everyone into the same pile and then we randomly assign them to the groups and we kind of replicate these groups randomly over and over and over again. And then we compare, okay, well, what we saw compared to these simulations that we've done, right? What's the probability of what we saw, right? Or something more extreme than what we saw in our original sample. That is the p-value, right? It's just a different way of thinking about the p-value. So we talked about A/B tests, and today I'm going to talk about ANOVAs, which just is an extension into more than 2 groups, right? 3, 4, 5, as many groups as we want. Okay. But let's say, recall A/B testing, right? Compares 2 groups. Right. And that can be numerical or categorical. And with permutation tests, it actually doesn't matter, right? Because we just measure whatever metric we're interested in, and then we go for it. Go for it, as if that means anything. Right, but then we can look at these simulations and we can figure out, okay, what proportion of outcomes were more extreme than what we saw in our original sample. And then that's how we would find our p-values. We're going to do the same thing with the ANOVA, except now we have multiple groups. Okay. So here we're comparing 2 groups. Right. So what if we have more than 2 groups? If there's a numerical variable in there, then, right, a numerical and a categorical variable, then we're going to have what we call an ANOVA situation. Okay. If one of the, maybe I'll say, if the measurement is numerical, across groups, right? And the groups are categories, right? Categorical variables. Then we use an ANOVA to compare more than 2 groups. Then we use an ANOVA to compare means across more than 2 groups. Across more than 2 groups. If we had to visualize it, right, then we would make probably a side-by-side box plot or something similar, maybe something fancier. But essentially, we're pretty good with a side-by-side box plot. I'm going to steal one from the textbook here. Oh boy. Hopefully I didn't go too far. Sorry, guys. Oh man. Blah, 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 blah. No, blah, blah, blah. We've talked about all this. I just want that side-by-side box plot. Oh, I wrote that. Here. Oh. So here, just as an example, I'll make it really small, but zoom in just to keep it on the same page here. Yeah. So for example, if I'm talking about the time that, I don't know, I guess people spent on different websites, right? Then I have categories, page 1, page 2, page 3, page 4, right? I've got a couple of options if I wanted to compare these groups, right? Are these significantly different from each other, right? If we just use the tools that we have, right? I could use pairwise t-tests, right? I could see if page 1 is significantly different from page 2, or page 1 is significantly different from 3 or 4, right? 2, I've done 2 and 1, but I haven't done 2 and 3, 2 and 4. 3 and 4, I think that's it. Right? That's a lot of different combinations, right? So we could we won't, but we could do pairwise comparisons of the 2 pages, or sorry, of the 4 pages. Right, page 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. I think those are all the possible combinations, right? But each of these would involve a t-test, right? Or something similar, right? You could do a permutation test, but we're kind of more comfortable with just a 2 sample t-test, right? And so here, right, I could do a two sample t-test. And I would be doing that 1, 2, 3, 4, 5, 6 times over, right? But every time that I run that test, right, I'm saying I'm okay with a 5% chance of a type 1 error, right, with my alpha level. So every time that I run this test, I'm saying, yep, I'm fine with a 5% chance. But now all of a sudden I'm doing it 6 times. So now all of a sudden the probability of making a type 1 error is huge, right? And so we don't want to do that. Okay. And so in running, oops. Is it only 6? 1, 2, 1, 3, 1, 4. Did I do them all? 2, 3, 2, 4. All right, whatever. In running 6 different t-tests, or permutations, there's an alpha level probability of making a type 1 error every time. There is an alpha level probability of making a type 1 error every time. Right? So then all of a sudden you have this large probability of making a type 1 error, right? And so there's a couple of different ways that we could deal with this. Even if we didn't want to do an ANOVA, which is kind of the natural choice, then what we could do is we could do, and there's lots of different corrections that you can make, but one of the most common ones that we would do is a Bonferroni correction, which basically takes the alpha level of 0.05, right? Because you want to keep it at 0.05, but then you split it across the number of comparisons that you're making, right? So it's just one way that you could deal with it. You could do pairwise comparisons. It's fine. I have it here, so I just want to there are many ways to adjust for multiple comparisons, right? Or to adjust for multiple pairwise comparisons. I guess I'll just say comparisons, right? But the simplest is the Bonferroni adjustment. But the simplest is the Bonferroni adjustment. which just says that the adjusted alpha level is your kind of original desired alpha, which is usually 0.05, divided by the number of comparisons. The reason I mention this is because eventually we will do these pairwise comparisons, because the ANOVA is only going to tell us if there is a combination in there that has a significant difference. So it won't tell us which one. And so then if you find that there is one in there, or at least one in there that's significantly different from another one, then you would need to go down this route of considering the pairwise comparisons, right? But not unless the ANOVA tells us to. And sometimes it's enough to just say that there is something in there that's significantly different. Oh yeah, so then the adjusted alpha that we would use is just typically just take your alpha divided by the number of comparisons, so 6 in this case, and then you're off to the races, and then that's your new alpha level, right? So before we conduct all these pairwise comparisons, right, what we would want to do is we run an ANOVA just to see if there is anything significant in there. So before we run the pairwise comparisons, we usually run an ANOVA first, which tests now. I haven't really done this with you guys yet, but usually all we need to talk about a test or a significance test is I need to tell you what the null hypothesis is and probably the alternative hypothesis. And then you can kind of go from there. And then I'll need to probably tell you the test statistic, right? And then you know the rules of the road for doing a hypothesis test, right? We're going to swap out that calculation, right? We're not going to do that nasty calculation because we're either going to use R or a permutation test, right? But the idea stays the same, right? We set up our hypotheses, we still do that. Then we do the test, which is either a permutation test or kind of calculate the test statistic. And then we get a p-value regardless of how we got there. And then we can draw our conclusion based off of that p-value, right? So the structure is the same. It's just that little midsection, the calculation part, that it changes a little bit. So the null hypothesis for an ANOVA is that mu1 is equal to mu2, which is equal to mu3, which is equal to all the way through to some arbitrary mu k. Right, just placeholder for however many mu's you want. Yeah. The alternative hypothesis is that at least one of the mu i's is not equal to mu j. At least one mu I is not equal to mu j. So here it just says, yep, there's something going on in here, right? I can't tell you which one. You'll have to do more work to figure out which ones or one. So here, notice it does not tell us which pairs, potentially more than one, which pairs are significantly different from each other. are significantly different from each other. Okay. So then, and the textbook does talk about the F test, right? So the F distribution is what we would use. But I want to talk about the permutation test just to show you that it's going to be the same as for if we just have two samples, right? But now we're just divvying them up into more than two samples. And to save us a little bit of writing here, I'm going to steal this. I know it's cheating, but we want to know if the puppies are still in the S building. So here we're talking about an A, B, C, D test, right? We've got 4 possible outcomes. Or 4 groups. Web page stickiness is referring to how long people are spending on each website, right? And so if we're going to do this permutation test or resampling procedure, we kind of use them interchangeably. For more than 2 groups, we follow the same procedure, right? We combine all the data together in a single box. So we record what happened in our original sample. And now we want to know, okay, well, how extreme is that? So then you throw all your data back into a single box. And then you shuffle, of course, and then you randomly draw out 4 resamples. And I guess this one had 5 values each, but that's not necessarily always true. Of the same sample size as the original, right? You're just replicating the original sample that you collected, right? You don't necessarily have the same sample size for each group. That's fine, right? But usually we do, but because we're assigning them to different groups typically, right? But you're just replicating the different groups that you have. So then you're going to record the mean of each of the 4 groups, right? You're going to jot that down. R is just going to store it in some array somewhere, right? And then you're going to record the variance among the 4 group means, right? And so now you have these 4 means, right? And there's some variance between those means, right? And so you're also going to record that. Okay, and that part, I think, is why it gets a little bit more complicated, but don't worry, there is an R function that we're just going to use and apply. So don't worry, you're not going to have to do this step by step like before, but, and then we repeat this 1,000 times, 1,500 times, whatever. And then the proportion of time that the resampled variance, right? So this variance from step 4, right, exceeded the observed variance, that's going to be the p-value, right? So it's not actually looking at the means, it's looking at the variance among the means. And so it's kind of weird. Okay. So here, it's a little bit more involved, right? Because we're recording the mean, but we're also recording the variance. And so luckily there's this LM-PERM package that's going to do it for us. Sure. Copy. Just steal this. Okay. So the LM-PERM package is going to do the permutation test for you, right? And so the AOVP is the permutation ANOVA. And you don't tell it how many permutations to do, unlike the other permutation tests that we haven't done in the lab because we're a little bit behind, but we will, obviously. Right, it just needs what the variables are and the data set, and then it just kind of goes for it. So it sets it up as a typical ANOVA output, except it has the number of iterations that it did as well. So in this case, 3,104. And then we have this probability, right? A p-value of 0.09278 tells me that there's nothing significant happening between these groups, right? What I saw was not that extreme compared to my random samples, right? So, good. If we did the same thing, but using a structured ANOVA, which is using the F-test, right? So it's kind of going back to that traditional space where, okay, we've got this F distribution and I'm going to calculate an F-test statistic and I'm going to use the F table. Usually there's a table or some F distribution, right, to find the p-value. What we're going to find is that the p-value is quite similar. And I'll steal it just so we can look at it. Right. If we compare these two. So just the AOV is that traditional ANOVA, right? And it takes the same input, which is kind of interesting. So it just depends on how you want to do it, right? But the AOV is just going to run this test, this F test. And so it calculates an F statistic, which is the mean squared for the treatment divided by the mean squared of the residuals, right? This divided by this. And I don't know, I can't remember how far we got, but we can figure out all these components, but we just need to be able to read it, right? And so, and they're all related, but the F value, and then it gives us the P value. So here, right? This is not that different from, what was it before? 0.09278 from the permutation version or from the permutation test. Right, just different ways of getting there. Right. So for us, of course, I feel more comfortable working with the F-test, and because that's how I was raised and just kind of, that's what we were doing, right? But for us, I want us to focus more on the permutation version, right? It's good to be able to compare these values, right? Notice that the output here is basically the same except for some rounding, right? So the actual values are the same, but it's just whether we calculate an F value or if we're doing iterations, right? That's the only difference. Yeah, and okay, good. Just as a heads up, there's a one-way ANOVA and a two-way ANOVA. This is a one-way ANOVA because we're only considering one set of groups. If we had groups within our groups, that would be a two-way ANOVA. But let's just stick to one-way ANOVAs for now. But let's talk, I'll just outline what they are so we have them. Oh. I'm used to standing up, moving around. So one-way ANOVA is going to compare, and maybe I'll just underline it here. Compares numerical data across groups from one factor. Compares numerical data across groups from one factor. For example, maybe the average commute times over the days of the week, I think is what the textbook uses. The average is from the numerical portion, and then the days of the week would be the factor. Average commute times over days of the week. Versus the two-way ANOVA. If you wanted to introduce another factor, right? And so the days of the week, you're likely, so commute times over the days of the week, if you just consider all the days of the week, then you're likely going to find a difference because the weekdays and the weekend are going to be different. So then your F-test is just, or your ANOVA is just going to be significant always, right? So what if you wanted to introduce another block that says, okay, these guys are in the weekdays and these guys are in the weekend, right? Now, is there a difference here? Right, so you're just introducing another layer, kind of making it more complex, but to think about. But in general, it compares numerical data across groups from two factors. For example, average commute times over the days of the week. And broken up by weekday or weekend. Right. Or maybe the season. Or something like that, right? Maybe the summer months are different from the winter months, right? That kind of thing. Okay. We've got notes about degrees of freedom, but yeah. Degrees of freedom are just how many things are allowed to vary, but you can read all about it in the textbook. How about that? It's not important for us. Let's end there. What do you think? Let's go see those puppies.
It's still 1:30.
Then we gotta go.
It starts at 1:30.
It ends at 1:30.
Okay, get out of here.
I think it started at 11.
Either way, it's worth checking out. Let's finish here. If you have any questions, let me know, of course. Otherwise, have a great weekend. See you on Tuesday. Stop this.